Okay, welcome back to video number 2 for chapter 18. We're talking about sampling distributions. So what can go wrong? Don't confuse the sampling distribution with the distribution of the sample. We already talked about this a little bit, but let's talk about it a little more. When you take a sample, you get data, you look at the distribution of the values, usually with the histogram, and you may calculate summary statistics. That one of the summary statistics is the p-hat. The other one, and that's when you have categorical data. When you have quantitative data, you would probably calculate y-bar, calculate the mean. The sampling distribution is an imaginary collection of the values that a statistic, the p-hat or the y-bar, might have taken for all random samples, the one you got and the ones you didn't get. So they're different. Beware of observations that are not independent. The CLT depends crucially on the assumption of independence. You can't check this with your data. You have to think about how the data were gathered. Randomness is our big clue as far as independence goes. Watch out for small samples from skewed populations. The more skewed the distribution, the larger the sample size we need for the CLT to work. So with the pennies, really that n equals 20 might be large enough for the CLT to work. It would be better if n equaled 40 or 50. Okay, let's go on to examples. And the first example we're going to look at is problem 17 on page 434. Best known for its testing program, ACT Incorporated also compiles data on a variety of issues in education. In 2004, the company reported that the national college freshman to sophomore retention rate held steady at 74% over the previous 4 years. So 74% of freshmen went back to the same school for their sophomore year. Consider random samples of 400 freshmen who took the ACT. Use the 68, 95, 99.7 rule to describe the percentage of those students we expect to return to that school, whichever school they go to, for their sophomore years. Do you think the appropriate conditions are met? That's going to be the last. So we've got two things to do. First thing we're going to do is the 68, 95, 99.7 rule. All right, so I've shrunk up the problem there where you can look at it. We're looking at a normal distribution centered at the population proportion and with a standard deviation equal to the square root of p times q over n. All right, so first thing we look at and go, okay, the mean proportion, the true proportion of the whole population is 0.74. So that's going to be the mean of our distribution. And then I have in there the values 0.74 times 0.26 because Q is going to equal 1 minus 0.74, so 0.26 divided by 400 because that's our sample size, and that gives us a standard deviation that rounds to be 0.022. So went ahead and put my mean on my horizontal axis. So now I'm going to start subtracting the standard deviation and adding the standard deviation to that mean. All right. So I found those values where, going from left to right, I've got 3 standard deviations below, 2 standard deviations below, 1 standard deviation below, then the mean, and then 1 standard deviation above the mean, 2 above, and 3 above. So let's put in the 68, 95, 99.7. All right, so 68% of the observations of the p-hats from 400 students would be between 0.718 and 0.762. 95% of the p-hats of 400 randomly selected freshmen would be between 0.696 and 0.784. And 99.7% of all of the p-hats proportion returning to their school for their sophomore year of random samples of 400 freshmen would be between 0.674 and 0.806. All right, do you think the appropriate conditions are met here? So randomization condition. Although not simple random samples, the problem does state that the samples are random samples of 400 college freshmen who took the ACT. It is plausible that the samples are representative of all college freshmen who took the ACT. Now, I don't know that you could say that it's representative of all college freshmen, period, in case there is something different about college freshmen who took the ACT than ones who did not. Okay, but we can make generalizations here to all college freshmen who took the ACT, the population from which the random sample was selected. 10% condition, it's reasonable that there are more than 10 times N, 10 times 400, 4,000 college freshmen who took the ACT. Thus, the sample is no larger than 10% of the population. Okay, the population is at least 10 times as large as the sample. The sample is no larger than 10% of the population. Logically, those mean the same thing. Okay, success failure condition, we need to make sure that at least 10 students from our sample would be expected to be successes to actually go to the same school their sophomore year, and at least 10 would be failures, would fail to go to the same school their sophomore year. So since the number of successes N times P, 400 times 0.74 equals 296, and the number of failures N times Q equals 400 times 0.26 equals 104, or they're both at least 10, the sample size is large enough for our methods. Guys, notice it took some writing to check these conditions and demonstrate that I know what I'm doing with them. You're going to need to do the same thing. I know it's kind of a pain, but it's necessary. Because remember, part of the goal is for you to be able to use statistics well in the wild, not just in a classroom setting. And you're going to have to check to see if a certain situation meets the conditions for a particular method. Okay, so that's what we're trying to train you to do. All right, so let's move on to exercise 19. Based on the 74% national retention rate, does a college where 522 of 603 freshmen returned for the next year as a sophomore have the right to brag that it is an unusually high retention rate? Okay, so for this, we've got to consider the distribution where N is 603. Previously, we considered where N is equal to 400, but we need to consider the sampling distribution where the sample sizes would be 603 because that's how many freshmen are involved in this particular scenario. So let's see how many standard deviations above or below the mean the observation is, and that'll give us an idea of if it's unusual and unusual in a good way or unusual in a bad way, if it's something typical, because the only reason they'd be able to brag is if it was unusual in a good way. All right, so we have to consider the appropriate normal distribution centered at P and with the standard deviation of square root of PQ over the appropriate sample size. So in this case, we're talking about the normal distribution centered at 0.74 with a standard deviation of 0.74 times 0.26, all divided by 603. So our standard deviation is actually a little smaller here with a standard deviation of 0.018. Our observation is reported to us as 522 of 603. We need to divide to get the sample proportion. Okay, we don't want to leave it just as a raw number. We want to figure out what the sample proportion would be. So P hat is 522 divided by 603 is 0.866. So that is larger than the average, 0.74, but the question is how much larger? We need to know how many standard deviations. Now let's determine the number of standard deviations above the mean of 0.74 our observation 0.866 is. In other words, we're going to find the z-score. That is exactly what a z-score means. So it's going to be our statistic minus the mean over the standard deviation of the statistic. So it's P hat minus P over the standard deviation of P hat. And so we've got 0.866 minus 0.740 divided by 0.018, and that turns out to be 7. Well, 7 higher than the mean is a great thing here. So, I mean, that's just kind of amazing. Any observation standard deviations above the mean is unusual. In this case, in a good way, you want to retain your freshmen to be sophomores. So yes, the college has reason to brag. Now, earlier we said that we can determine likelihoods. So we can determine a probability associated with this. How likely is such a rate? Oh, I have a little typo there. I should have A there. it's going to be the probability that z is greater than or equal to 7. So we would do normal CDF because this is a normal distribution from 7 to infinity, and it's approximately 0, so it's not likely at all. This is amazing. Okay, so we've looked at proportions. Let's look at sample means. Assume that the duration of human pregnancies can be described by a normal model with mean 266 days and standard deviation 16 days. We're going to consider several questions here. The first one is what percentage of pregnancies should last between 270 and 280 days? So we're not averaging anything here. We're just looking at the quantitative data itself. And so we are considering the distribution of the original population. Okay, so our z here is just going to be y minus mu over the standard deviation of y because we're looking at individual pregnancy lengths. And so that's going to be 270 minus 266 all divided by 16 is 0.25. That's our lower bound. Our upper bound is going to be 280 minus 266 over 16, and so that's going to be 0.875. So we're going to get the probability that we're between the lower bound and the upper bound. Originally, it was 270 and 280 days. In terms of z-scores, it's 0.25 to 0.875 because 270 days is a fourth of a standard deviation above the mean, and 280 days is 0.875 standard deviations above the mean. Normal CDF from 0.25 to 0.875 is 0.2105, so 21.05% of pregnancies are between 270 and 280 days. At least how many days should the longest 25% of all pregnancies last? So this is giving us area underneath that normal curve. Okay, remember, longest 25% would have an area of 0.75 to the left and an area of 0.25 to the right. So the z-score associated with this is going to be inverse normal of 1 minus 0.25, so inverse normal of 0.75, which is 0.67. So if 75% of the pregnancies are shorter than this and 25% are longer, do you remember what that's called? Yeah, it's the third quartile. And so the third quartile always has a z-score of 0.67 for a normal distribution. All right, so z is going to equal y minus mu over the standard deviation of y because we're still dealing with individual pregnancies. So 0.67 equals y minus 266 over 16. Multiply both sides by 16 to get 10.72 equals y minus 266. Add 266 over, and you get 276.72 equals y. So the longest 25% of pregnancies last 276.72 days or longer. Suppose a certain obstetrician is currently providing prenatal care to 60 pregnant women. Let y bar represent the mean length of their pregnancies. According to the central limit theorem, what's the distribution of the mean y bar? Specify the model, meaning is it normal, binomial, geometric, what's up with that? The mean and the standard deviation. Okay, so we are no longer talking about individual pregnancies. We're talking about sample means. Okay, so we're talking about the sampling distribution of sample means when n equals 60, because this doctor is seeing 60 pregnant women, and we're talking about the mean length of all 60 women's pregnancies. So the model for any the sampling distribution of a sample mean is going to be normal with mean mu, okay, the same mean as the individual observations, and a standard deviation equal to sigma over square root of n, where sigma is the standard deviation of the population of observations, the original population. So in this case, it's going to have a normal model with a mean of 266 and a standard deviation of 16 divided by square root of 60, which rounds to be 2.07. So the work I've shown along with that final statement is sufficient. You do need to show the work. You need to show the formula for what you're finding and the plugged in values, and then you can give the final answer. but it is enough to put that capital N and then parentheses 2.66 and 2.07. Everybody knows that that means normal with a mean of 266 and a standard deviation of 2.07. But you do need to get used to writing down the formula part, the plugged in values, and then what it simplifies to be, so that you'll get full credit on the AP exam. So what's the probability that the mean duration of these patients' pregnancies will last at least 260 days? So we're not talking about a single pregnancy lasting less than, did I say at least, will last less than 260 days. We're talking about the average of 60 pregnancies lasting less than 260 days. So we want the probability that Y bar is less than 260. We're talking about an average. So we need to convert an average to a z-score. So that's what this little arrow is. Oh, okay, we've got this in terms of Y bar. Let's get it in terms of z. So z is going to equal Y bar minus mu over the standard deviation of Y bar. So that's 260 minus 266 divided by that 60 over square root of 16. And I wrote it in that form just to remind you of how we got the standard deviation of Y bar. 260 minus 266 is negative 6 divided by 2.07 gives us negative 2.90. So an average of 60 pregnancies of 260 is 2.9 standard deviations below the mean. Okay, so now we take that z value and we plug it in since we had Y bar less than 260, because that's less than 260 days. We write an analogous statement using z. So we want the probability that z is less than negative 2.90. And so that gives us 0.0019, so 0.19%. The duration of human pregnancies may not actually follow the normal model described in exercise 37. Explain why it may be somewhat skewed to the left, and then we'll consider question B. Well, there are more premature births than there are extremely long pregnancies, so that's why it might be skewed to the left. Doctors typically do not let a woman go more than 2 weeks past her due date, but sometimes babies are just born really, really early. Okay, so if the correct model is in fact skewed, does that change your answers to parts A, B, and C of exercise 37? Explain why or why not for each. Yes, for parts A and B, as they rely on the normality of the distribution of individual pregnancies. Okay, so when you're talking about individual observations, you have to have a normal model. No for part C, because the central limit theorem guarantees a normal model for the sampling distribution when the sample size is 60, even if the distribution of the individuals is skewed. So the central limit theorem saves the day for the averages there. Okay, guys, that is it. I can't wait to see you in class next time, and we'll do the chapter 18 rounds, and then we will move on to more based on the sampling distributions. Have a good day.